Okay. All right. Welcome everyone to the first seminar of the year 2024. And we haven't seen you at CGD seminar for a while. I hope you all had a great break, and I'm glad that you all survived this harsh weathers in the past few days and came up here. Today we have our speaker, Yuan from Columbia University and NASA GIS. And she got her PhD from National Taiwan University in 2022, where she studies mostly large-scale dynamics with a focus on the interactions between ocean, clouds, and radiation. And after getting her PhD, she got on to her current position, where she focused on the cloud feedbacks in the past, present and future climates. And she is going to present part of her recent work in today's presentation. Without further ado, let's welcome Jen. She goes by Jen. Yeah.
Thank you everyone for coming. I'm currently a postdoc at Columbia and NASA GIS. So today I want to discuss about the time evolution of local feedback. I will focus on how to quantify the relative importance of the forced and unforced signals. This research is collaborated with Greg Cesana. Me and Greg are both at Columbia and NASA GIS, and Christy at UIUC, Mark at Lawrence Livermore National Lab, and Kyle Ammer from University of Washington. So let's get started. Let's start with how climate feedback has changed in the past. So here you're looking at the time evolution of the net radiative feedback, estimated in a sliding 30-year windows from a group of AMIP high forcing simulations, which means we have AGC and we prescribe them with observational sea surface temperature and sea ice, and the forcing is fixed at pre-industrial levels. So through this time evolving observational SST and sea ice, we see ups and downs of the net radiative feedback. And especially for the past 50 years, we see this negative trend of the feedback. So the net radiative feedback has become more insensitive and is getting more and more inconsistent with the feedback estimated from CO2 quadrupling simulations. If we decompose this net radiative feedback into different components, the cloud feedback is not the one who has the largest magnitude, but it is the cloud feedback that contributes to this time evolving net radiative feedback. So what are those possible processes that could contribute to the time evolution of climate feedback? Here at Canuti et al. 2017, they list a bunch of factors that could potentially contribute to a time evolving climate feedback. So I will go through most of them. And let's first start with base state dependence. So one example for base state dependence of climate feedback is here I show Seiler et al. 2018. They are correlating the present day AMIP cloud contribution to albedo to the future warmer 400 CO2 global cloud feedback. So here's a correlation map they're showing. And this correlation map looks like climatological SSE pattern with a flip sign. So in those climatologically cold SSE regions like Etrotropics and Eastern Pacific, this positive correlation means with the higher the present date cloud contribution to albedo, for example, more low clouds, then it will correlate with the higher, more sensitive global cloud feedback from 400 CO2 simulations. While in climatologically cold warm SSE regions like Western Pacific, then this correlation is opposite. This is one example for the base state dependence. And also forcing can affect the time evolution of feedback. Here, Salvi et al. In their recent research shows that different forcing agent could lead to different magnitude of climate feedback. So here they use a set of single forcing simulations. So on the blue one is the aerosol only simulations and greenhouse gas only and natural forcing only. And the green one on your right, this is the historical forcing with the full set of forcing agents. So the idea is with different forcing agents, we might have different magnitude of radiative feedback. So say if we are transitioning from a aerosol dominant time period to a more like greenhouse gas dominant time period, then the feedback can change just because the mixture of the forcing agent is different. Also, let's move on to the changing warming pattern, aka pattern effect. I think it's one of the active fields in the past few years. And the idea is the radiative feedback depends on the spatial distribution of the SST. And one quantification for this pattern effect is through using SST Green's function. So basically, you run a lot of AMIP type simulation. Each one you force AGCM with warming or cooling in a local patch of SST, and then diagnose the TON net radiation. So here is the sensitivity map of those, a set of the Green's function simulations. So this sensitivity map shows that if you warm 1K in Western Pacific, and you will efficiently increase the low level stability in the whole tropics and grow the low clouds, and that so the more solar radiation get reflected, and which correspond to a strong negative feedback if we warm 1K in Western Pacific. On the other hand, if we warm 1K in Eastern Pacific, usually you just locally decrease the stability and decrease the local cover, and that will correspond to a positive but weaker climate feedback. So this Green function helps us to quantify how radiative feedback might depend on the spatial pattern of the surface warming. The third one, I want to talk about the internal variability. So here I'm showing Rockwell's 2021 work. They conduct the low frequency component analysis in 35 76 pre-industrial control simulations, and they identify the 3 low frequency patterns shown as the top 3 rows, and also the least low frequency components, a higher frequency component, which looks like ENSO. And they did show that if they use NEO 3.4 index, they will get very similar results. The idea is we get this low, high frequency patterns, and they will correspond to different Lie correlation of the global mean surface temperature and global mean TOA anomalies. This is the Lie correlation onto each pattern, onto each mode. So, from their research, we know that pre-industrial, we know that the internal variability contribute to the change of the climate feedback, because each mode, either high and low, they have their specific relationship between the TOA radiation and surface temperature pattern. So if we have phase change of the internal variability, or we're shifting from, or we have different dominance of the high versus low frequency variation, then the climate feedback might be affected. So I have go through most of the factors that will contribute to the time evolution of climate feedback, but I want to point out that these processes are not independent. They could relate to each other. One good example is from Zhou et al. 2023. They try to explain the forcing efficacy, which means global mean temperature increase per unit change in specific radiative forcing. And they explain the spread of the forcing efficacy with both pattern effect and state dependence. And here in our research, we want to focus on both internal variability and changing warming pattern. So considering both internal variability and the pattern effect, our question is, how would the forcing and internal variability combining shape the time evolution of SSE pattern, and that would further translate into the time evolution of cloud feedback? That's basically our question for this research. I will show the main result first, and then I will show this later. I will show this figure again later, but I want to show the main conclusion from this research. I will fill in the details later. So this is the time evolution of the local feedback due to estimated inversion strength changes, estimated in CSN2 large ensemble. So the black line is our goal. This is the overall local feedback changes from pre-industrial in a period to the end of the century. So you see that the local feedback becomes more negative in recent decades. And we want to explain this time evolution of local feedback. And the red and blue line is the forced and unforced component of this local feedback, EIS-induced local feedback. And as you can see, for the 30 years windows ending before the 80s, the overall local feedback, the black line, is mostly influenced by its unforced component. So the black and blue lines are really close. While for 30-year windows ending after the 2010s, then this overall feedback is mostly influenced by its forced component. So it seems like before, like for the 30-year windows ending after the 80s, but before the 10s, we are in the transition period where the feedback is transition from being dominated by unforced signals to being dominated by forced signal. And later we will show the quantification, but the idea is this relative importance between the forced and unforced is just determined by their relative magnitude of the global mean temperature variance. So in the next slide, let's derive this equation that we use to quantify the forced and unforced contribution to the regressions. Okay, so here, this is a math slide. Our goal is to quantify the forced and unforced contribution for the ordinary least square regression. So for each, say, 30-year window, if we regress the variable x against the global mean temperature, we write it as dx, the global mean temperature. The ordinary least square regressions, the definition is the covariance between the two over the variance of the denominator. Here's global mean temperature. So for most of the case, say if the variable x is radiation, this is climate feedback. For most of the case, either global mean temperature or radiation, they will consist of two components. The forced one is written as subscript F, and the unforced one is subscript U. And if we just decompose, if we substitute a full response of the variable x and global mean temperature, we can write the regression as the second line. If we expand it, we get the third line, and then now we have covariance between the forced and also the covariance between the forced and unforced. So the only assumption we make through this derivation is we assume that the covariance between the forced and unforced response is very small. So the idea is, we will verify this later, but the idea is we are not expecting the one CO2-induced global mean temperature covary with the Ansel variability-induced temperature change. It's a basic idea. And so if this assumption holds, then these three terms are really small, and we can lump it to a residual term sigma here. And that's good for us, because then the only thing left are the covariance within the forced x and forced global temperature and the unforced one. We kind of separate the two. In order to linearly separate these two components, we just have to rewrite this equation. So I hope this is clear, but these two cancel out. So the fifth line is just the rearrangement of the fourth line of the equation. So if we identify this is a variance of a forced global mean temperature over the sum of the forced global mean temperature and the unforced global mean temperature. this is the number between 0 and 1. And if we identify this ratio as R, then this must be 1 minus R. And this is the forced component of the radial feedback, and this is the unforced component of the radial feedback. So now we kind of decompose. The final form of this derivation is for each of the ordinary least square regressions, we can decompose it into forced and unforced part. And it's just a weighted sum between the two components, and the weighting is only determined by the relative magnitude of the global mean temperature variance. So here, say, because global mean temperature the global mean temperature is just a time series, so it really just a time evolving weightings between the two.
May I ask a question
Yeah.
to clarify?
Yes, go ahead.
Thank
Yeah,
you so
because
much.
we have the
I'm a
same-
little confused about the unforced global temperature that we think of as being associated with, for example, El Nino, La Nina. So how can you make that assumption that, or maybe I'm missing what your assumption is? I would think as CO2 goes up, forced temperature goes up, and in many models, and unforced, and so variability also goes up. So the unforced global temperature component would also increase.
So we do calculate this, and
Okay.
it's like way smaller than
Okay.
the other terms. We will show this later. We test 3 large ensemble that we will show, but you're right, this is the assumption that we have to make. So since the variance of a global mean temperature is important for the relative importance of the forced and unforced. Here we're just showing global mean temperature from 3 large ensemble simulations, CSM2, MPI, and GIST model. And the red one is the forced global mean temperature, so ensemble average. And the blue one is the relative anomalies to this ensemble average. So there are like 100 lines for CSM2 for your blue line, but the red line you only got 1 because that's ensemble average. And the variance of the global mean temperature here is on the second row. So note that this is the year, absolute year, but this is the end year of the 30-year moving window for variance in the 3 large ensemble simulations. And I drew 2 vertical green lines here, which is the end year of 2080s and end year of 2010. So that's the 2 time period that we'll focus on in our later slides. But you can see before the first green line, the variance of the unforced global mean temperature is larger than the variance of forced global mean temperature. And after the second green line, like the variance of the forced global mean temperature keeps strengthening, and then will take over the unforced global mean temperature variance after the 2010s. If you just plot it as a relative magnitude, as an R that I showed in the previous slide, the R is the numbers between 0 and 1, and R is, it's just an index to express how important the forced component is. So before the 30-year windows ending, before the 80s, the R is around 0.2, 0.3, and after 2010s, this goes up to like 0.7 in CSM2 and 0.6 in GIST model. So it really shows that in the meantime, like in the past 50 years, we are transitioning from a unforced dominated time period to the forced dominated time period. And I'm also interested in the ups and downs, before the windows ending after the 80s. So you can see the 3 large ensemble, they both share some similar characteristics, which is they have ups around on on the end of the last century.
1900.
And so this is because if you see if you look up for the previous major volcanic eruption, you can see there are two major eruptions around that time that is included. So in that time period, you will see larger contribution from the force part. And also, like between the 1920 to 1960, we have a period of 30-40 years where we don't have major volcanic eruptions in the historical record, and we also see that there's a local minimum around 1960. The x-axis is the end year of 30-year window. So the end year of 1960 is the correspond to the time period where we have less major eruptions in the past. Okay. So I hope I have kind of convinced you that the overall feedback is can be determined by the relative importance of the force and non-force feedback. So in like either CSN2, MPI, or GIS, you can always see that the black line is drawing from blue line in the past and to the red line in recent decades, and that it will get very close to red line till the end of the century. So whether the overall climate feedback is going to increase or decrease, that depends on the relative magnitude of the forced and unforced feedback. If, say, in CSN2, usually the unforced feedback is more positive than the forced feedback, then the increasing importance of the forced feedback is going to contribute to the decrease of the overall feedback. But if, say, in MPI models, their SST component, the forced one is more positive than the unforced one, then in this case, the increasing importance of the forced feedback is going to contribute to the overall increase of the local feedback. Right? And if, say, GIS model is really weird, the local EIS-induced local feedback, the unforced and forced one, their magnitude is very similar. So even if they have increase of the relative importance of the force, it's not going to change the overall feedback. I want to highlight the range of the y-axis. So the EIS-induced local feedback here, the y-axis is 3 times larger than the SSC component. So the overall local feedback contribution is coming from EIS component. So for CSM2, we have more negative cloud feedback in the past 50 years, and that's from EIS, and that's from the change of the relative importance of the forced and unforced feedback. So I want to point out that our goal of this research is to quantify the relative importance of the forced and unforced SSC patterns onto the local feedback time evolution. So the way we estimate local feedback through convolving the SSC pattern and EIS pattern with this meteorological radiative kernels from observation, and this is time invariant, and they have 4 observation data sets. We use the average of the 4. So the advantage of multiplying our time evolving SST or EIS with this time invariant kernel is just to isolate the role of the SST or EIS pattern, so that for every time evolution you see in the slide is coming from SST and EIS, not coming from the radiation sensitivity to the background climate state. And for the difference among the 3 large ensembles is also coming from their intermodal difference of the SST and EIS, not from their radiative sensitivity to each cloud controlling factors. Okay, so that's let's move on to the role of pattern effect since we have isolated the role of SSE and EIS. So here you're looking at the CSM2 large ensemble, the SSE pattern, the full SSE pattern, so DSST, D global mean temperature, and the forced component and non-forced component, and their residual. So it just follows the derivation that I showed before. Now you have to take the X as the original SST. So the overall SST pattern is also coming from the force and a weighted sum of the force and unforced. And the sigma here shows it represents the covariance between the forced and unforced. And I think that kind of answered Clara questions before. So the residual is quite small compared to the other three terms. And this is different time period. This is 50 to 80s, 80 to 10. And the bottom row, this is the end of the century. So we can see that the overall SSE pattern is moving from, looking very similar to unforced component to the end of century where the overall SSE pattern is just largely affected by the forced one. And then by the end of century, the unforced temperature, the SSE DTG is no longer contributing to the overall SSE pattern. Because in the end of the century, the R is reaching like over 0.9. So what is the implication for this time evolving SSE pattern? If we remember the SSE Green's function, this is Yuan's Ken4 SSE Green's function, and they identify an index to quantify the the relationship between the SSE pattern and net radial feedback. So they use this Western Pacific warming divided by the tropical average warming and say if we have higher relative Western Pacific warming, it efficiently decrease the net radial feedback. So the higher the index, the more stabilizing the net radial feedback you will get, just based on their results, right? And to apply their concept with our results, we calculate the SAM index shown here, and this is I call it IEP, like Indo-Pacific Western. Indo-Pacific way. Oh, sorry. So it's a SAM Indo-Pacific warm pool warming ratio. So in CSN2 large ensemble, this is a full one, the forced one, and unforced one in 50 to 80s and 80s to 2010s. So you can see the overall index is increasing because we are transitioning from the unforced one to forced one. The forced one is about 1 because we have very uniform warming for the forced component. So there's little difference between the Western Pacific warming versus the whole tropical warming. While in the unforced component, this number is very small because the Western Pacific warming is way less than the overall warming. It's cooler, it's cooler than the Eastern Pacific, and it's cooler than the whole tropical average. So you get a very small numbers. So if we are transitioning from the small number from unforced to the large number, close to 1 numbers from the forced, then we have to have this increase of the relative warm pool warming. And that corresponds to a more stabilizing net radial feedback. And it's consistent with the previous research. So that's only for CSN2 large ensemble. If we compare it with MPI and GIS, you will see that actually their force component, they look all very similar, around 1, which means their force component is just uniform. But the unforced component, there are some intermodal difference. CSN2 got the numbers around 0.3, but while the MPI and GIS got a number about like 0.7. So, if we compare their SSE patterns between the three large ensembles, I know there are too many figures, but the upper three panels are from CSM2, MPI, and GIS. And I just want to focus on the unforced component. So although they seem quite similar, they all show this ENSO-like SSE pattern, but the relative warming in the Western Pacific over the whole tropical average warming is quite different. For CSM2, this relative cooling is strong, but in MPI or GIS, you can see that the relative cooling in Western Pacific is weaker than CSM2, and that contributes to the previous higher numbers for their unforced component. And they also, because their difference in their unforced SSE pattern, and they will change the relative magnitude of the forced and unforced feedback. So that's why they kind of look different. For the EIS component, the forced one, for the three large ensemble, they at this are both negative, but for the unforced, for the blue one, the three large ensemble are not agree on the sign. For CSN2 is positive, is weak positive, but for MPI and GIS is negative. So it seems like there are some intermodal difference for the unforced component of the feedback. And it comes from the unforced SSE pattern because we have already isolate. We use the same radius kernels for each model, so it must come from their different SSE pattern. So with that different unforced feedback, you can see a slightly different time evolution of climate feedback. So for CSN2, there's a lot of difference between the unforced and forced. So if the relative importance of the forced component is strengthening throughout the past 50 years, we get this strong increase of the local feedback, while in MPI and GIS, this decrease of the local feedback becomes less obvious. So I hope I have convinced you about the local feedback that if we've estimated through ordinary least square regression, it can be decomposed into a weighted sum of the forced and unforced. So if we want to quantify the change of the local feedback, then it might come from the change of the forced feedback itself with no change in the R and no change in the unforced component. And the second one means the change in the unforced component with no change in R and F. And the third term is it's a contribution from the change of R without change of forced and unforced component. So we calculate the three terms is delta 1 and 2 and 3. So again, see on the change of, here we focus on the local feedback change between the 50 to 80s and 80s to 10, the two vertical line, and the SSE component on the top and the EIS component on the bottom. And again, we show that EIS contribute to most of the change of the local feedback. And these overall local feedback change can be attributed to the delta 3, which is the change of the R without change of forced and unforced local feedback. And so interestingly, the delta 1, which is the change of the forced feedback, actually give you the opposite sign. It gives you a more positive local feedback for the past 50 years, but it is the change of the R that contribute to the change of the overall local feedback. And GIS again, there's very weak change of the local feedback, and so it's not obvious to see which term really contribute to their change of the local feedback. And this is the local feedback difference between these two time periods. Now we want to compare the local feedback between the present day climate and the end of century. So now again, CEIS, the EIS-induced local feedback change is more important than the SST component. And now the dominant contribution is coming from delta 1, coming from the change of the forced feedback itself. I think it's like kind of straightforward because like between the present climate and the end of century, there's not so much change in the relative importance between the unforced and forced. So, so there's not going to be strong change in R. So we are not expecting a strong contribution from delta 3. While like in previous study, if we studied say 4 times CO2 simulations, we can see the changing in the feedback and we mostly attribute that to the force component because with a strong hammer from 4 times CO2 is mostly going to be the force component. So it's consistent with previous 4 times CO2 studies. It's coming from force feedback, the change of the force feedback. So that's a small summary. So from large ensemble simulations, we kind of explain why the overall local feedback might change just based on their time evolving relative importance between the force and unforced component. But in real world, we don't have large ensemble simulation for observation, and not every models have large ensemble simulations. So what if we do not have large ensembles? Then we trying to use linear trend as proxy of force responses and the detrended part as proxy of the internal variability. So it's definitely not the force versus unforced. We just try to use linear trend and detrended part to see how good is it. Okay, so how good or how bad is it if we use linear trend and detrend in observation if we do not have large ensemble. There's one method to test how good or how bad is it. It's just to use the same large ensembles because we already have force and unforced by taking the ensemble average and the relative anomalies of the ensemble average. And we can also take the linear trend to those large ensemble simulations. So we can compare the two and see how good or how bad is it to use the linear trend as the forced and unforced responses. So the upper row, this is the figures that I have shown before is from ensemble average anomalies. This is from linear trends and anomalies. So they definitely have good points and bad points. I'll start from the bad. The bad is we are hardly capture the ups and downs before the windows ending before the 80s. We can see the ups and downs mostly from volcano eruptions in 3 large ensemble, but if we use linear trend, it's really hard to capture that signal because the volcano eruption usually is strong, but it's within a short time period. So here we are using the 30-year sliding windows linear trend. So it's really hard to capture the signal from major eruption just using the linear trend. Most of the case, you would just ignore that contribution from volcano eruptions. So it for the years before. Sorry, yeah.
Just clarification. The pink shading and the blue shading are the lower lines of each ensemble member.
Yeah.
And the darker line is the mean of the ensemble members.
Right.
So should we, since we're testing whether or not having a large ensemble is useful or not useful, shouldn't we only be looking at individual ensemble members and not the mean of the ensemble?
The dark line is the mean of the linear trend.
Of all the ensemble members
Yes,
for
not
that
the
time?
not the,
So if you only had one ensemble member and you plotted it, how bad would it look?
Pretty bad.
Yeah.
Isn't that what we see in the thin lines?
Isn't that what?
Isn't that what we see in the thin lines?
Yeah,
Yeah.
exactly.
Yeah.
Yeah.
So each individual thin line is a bad realization of the linear trend model.
If it were that easy, we wouldn't do large ensembles,
Fair enough.
unfortunately.
yeah, so for each like individual line, it looks very like different. But I think the overall linear trend, there's still, we can see the pink line on the bottom, like, is raising from 0.2, 0.3. There's a lot of spread of ensemble spread, but it's increasing. And to the end of the century, the spread is narrowing. So the bad thing is we really cannot capture any like volcanic eruptions related signals in the previous record, but we do capture this transition, say, from very weak force or trend, very weak linear trend to like strong linear trend, and that's corresponding to very weak force response to strong force responses. So the good thing is we can capture this transition, but I think other than that, is the linear trend is there. It's very limited to use it as a proxy of the force responses. And so here I am plotting the R, and now R is from linear trend, the relative importance of the linear trend, not the force one. And from 23 symmetric 6 models, for each symmetric 6 model we use only one ensemble, and this is the NOAA reanalysis. So again, like for the 30-year windows before the 80s, we have very low confidence of what it really means. It's just a linear trend, sometimes very small, just because it's very noisy. But we do see an increase of the R, in both the symmetric ensembles, symmetric models, and NOAA reanalysis. They do have a, say, in NOAA is transitioning from 0.3 to 0.6 in the previous 50 years. And so do those semi-6 models. And here we are just conducting similar analysis, but now we only have to use the trend and detrend one, right? And this is the semi-6 model and the NOAA analysis for the SST component and EIS component. Let's start with semi-6 models. Again, the EIS component contribute to most of the change of local feedback between the 50 to 80s and 80s to 2010s. But it's not obvious which one is contributing to this overall change of local feedback. It seems like the delta 3, which is the relative importance of the trend and detrend component, contribute to the most of the negative trend of the local feedback. But the delta 1 and 2 also contribute a little bit of the change. And for reanalysis is strong that we only have one data point, right? So this is only, so I'm using the bar chart because we only have one reanalysis. And here the delta 1, which is the change of the trend part, is contributing to the overall negative change of the local feedback in reanalysis. And that is very different from what we have seen in the large ensembles. If we compare, this is our 3 observational SSE patterns in 50 to 80s and 80 to 10. But if we focus on the trend component, we can see that in in 50 to 80s, there seems like a hemispheric asymmetric SST pattern in both in all of the observational SST, but in the recent 30 years, 80s to 2010, there's a huge triangle shape Eastern Pacific cooling, and that this change of the SST trend contribute to the overall decrease of the local feedback in observation. That's different from what we have seen in either CMIC6 models or large ensembles.
Can I ask you a question about
Yes.
that? Not the previous one with the reanalysis. So that's not observations, it's reanalysis.
Yeah.
And should there be another component in your analysis to account for the non-conservation part of the atmospheric reanalysis?
Oh, yeah, yeah, that's a good question. We haven't tried that, but.
But aren't you just using the SST pattern and then convolving it with the Green's function?
With the radiative kernels.
Yeah, with the radiative-
So the difference between models and observation are only coming from their different SST patterns.
So it's just SST she's using, that's what I thought.
So, but the radiative kernel will not be impacted by the non-conservative terms?
You're not using your reanalysis radiation.
Right, she's using the observed, well, I don't know what she's using for the radiative kernels.
Series? Or-
No,
Okay, okay.
That's correct. We are only using the observational SST and yes, that's all. And the DR, DSST, DR, DEIS all coming from the observational meteorological radiative kernels. That is time variant, model independent, because that's the average of the present day observational DR, DSST, DR, DEIS. So for any time evolution, for any intermodal spread, for any discrepancy between model and observation, that's all coming from the difference of SST and EIS. So there are two possible explanations for the model observation discrepancy. So the discrepancy I'm talking is this different attribution of the local feedback. But because we are using trend and detrend component in reanalysis, it's not obvious that these changing in the linear trend is coming from the phase change of decadal variabilities, because this is a sliding 30-year linear trend. So it could involve the phase change of decadal variability still, but it could also coming from the models are just biasing the force responses. That is also included in the trend component. We don't have answer for this, but there are two possible explanations. So I am reaching to the conclusion slide. In this research, we are decomposing each ordinary least square regression, so radial feedback or SST patterns. We decompose it into the weighted sum of the force and unforced one, and the weighting is determined by the relative magnitude of the variance of the denominator. In this case, it's global mean temperature. Before the 80s, it seems like feedback or SST pattern is mostly driven by it's reflecting unforced responses. But in recent decades or in the end of the century, it's reflecting the forced responses. So even if we don't have any change in force or unforced component, we can have changing feedback only because we have this change in the relative importance. CSN2 and MPI and GIS, they have slightly different results, mostly because they have different unforced SST patterns. And observation, on the other hand, we see this negative trend of local feedback. But we can only attribute it to trend component, and we still don't know yet it's coming from the influence of multi-decadal variability or the change of the force responses. That's all. Thank you for
All right,
coming.
thank you. We're almost at the top of the hour, so we only have time for maybe just like one very quick question, and if you have others, please talk to the speaker afterwards. Any? Okay, yeah, Dan, go ahead.
I just wondered if you could talk about, so in this case, you have a feedback that responds to the changing climate. It seems like a kind of a feedback on the feedback. Is this, a way of kind of parsing the effects that you might see if you're diagnosing climate sensitivity from like a 4 times CO2 experiment, as attributing part of it to the evolving SST patterns? I guess I'm wondering, does this perspective, is this something that is missing from our, the way that we're currently diagnosing climate sensitivity from models, or is a way of maybe decomposing that?
In 4 times CO2, I am expecting very weak contribution from unforced responses, but in historical period, I think it's important for us to really separate the two or like investigate the unforced versus forced feedback. I think previous studies kind of assume that the change of feedback mostly come from forced responses, but here we just want to point out that it really can come from the change of the relative importance. But that's only happening when there is a change in the relative importance, right? In the future warming climates, we are not expecting there's a strong change in the R.
Okay, one last question.
I was
and then we're
wondering
done.
if you were, in your future work, would it all look at the relative roles of anthropogenic aerosols versus greenhouse gases? Because I think, when you talk about forced response, it's not just CO2, and each model has its different SSP, and the forced response, aerosols and greenhouse gases can kind of offset one another, and that could lower the importance of the forced response. So I just think that would be an important aspect.
We do think of that, and it's interesting. We have in my head, it's going to be going to be more complicated if we decompose those one. There's a lot of covariance, a lot of assumption we have to make. But it's right. We can decompose it into force
Just
components.
take single forcing large ensembles.
Okay.
Then you don't have to worry about all the terms, just within each one, what is the relative importance of forced and unforced? Maybe that's a way to step into it.
Yeah.
Okay, let's just thank our speaker again for. Yeah, if you have questions, like Jen will.
Yeah, I'll be around.
Yeah, so she will be around to answer your questions.
I guess, because we're starting 10 minutes late.
So lunch? Okay, I might crash your ocean scientist table. Sorry. What's the next book?